Let's take another example. And in this example we have a partial circular segment that is centered around the origin, and we want to find what is the electric field at the origin. Now we have the radius is some capital R, and the angle that um, the sector or circular arc part makes is theta naught above and below. So theta naughts are equal in magnitude. And we want to find the electric field at the center O. So let's draw our vectors. We're just going to extend this diagonal line. And if we go down, we have a y vector going down and an x vector going to the left. If I extend the other one towards the top, and I'm going to have a y vector going up and an x vector going to the left. And we're saying that there's a linear charge constant, so the charges along this tube are uniformly distributed. So that would mean that the y components are equal, and so they're going to cancel. And in this case, because of the orientation, my field is going in the negative direction, so I'm going to multiply my differential electric field by a negative cosine theta. The negative sign will tell me direction. Okay, so we have our differential electric field is equal to 1 over 4 pi epsilon naught r squared, and I'm going to have differential charge in the numerator. I have to figure out what this differential charge is. And normally we would say, well, lambda is equal to charge over length, or Q is equal to lambda times L. But now what am I looking at here? Well, I have some differential length on an arc. What is the distance of an arc? How do I determine the length of a circle or an arc? Well, in the case of a circle, arc length is equal to radius times angle. And this S is just my arc length, which refers to this L here. So now I have Q is equal to lambda times the length r theta. And if I do dq, then the only thing, this is lambda is a constant, r is a constant, theta is the only thing that I can do a differential of. So I have lambda r d theta. Now I can put that into my differential electric field. Oh, and I did forget my cosine of theta. Oh, negative cosine of theta. Sorry. Clean this up a little bit. Okay, so cosine of theta, and I have 4 pi epsilon naught r squared. Well, one of the r's are going to cancel, and lambda, 4 pi epsilon naught are constants. And so if I go to do my electric field, I'm going to take my constants out front, and I'm going to have r is a constant. I can take it out, and that just leaves me with the integral from negative theta naught to theta naught of cosine. Actually, I can take the minus sign out front too. Cosine theta d theta. So rewrite here, 4 pi epsilon naught r, and now I can do my integral. Well, the integral of cosine of theta is sine of theta from my limits, negative theta naught to theta naught. And then I'm going to have negative lambda over 4 pi epsilon naught r, and I'll have sine of lambda naught, or theta naught, minus sine of negative theta naught. Well, remember that I can use the property that sine of negative theta naught is equal to negative sine theta naught. And if I substitute this in, I'm going to get a sine theta naught plus sine theta naught, and that just simplifies my formula to lambda times sine theta naught. I'm going to have a 2 on the top that's going to cancel out 2 in the bottom, so I'm going to have 2 pi epsilon naught times r. This is my solution. So the biggest trick here, thing to recognize, is arc length. We are going to use this formula so much this semester. Please don't forget this formula. This is something that you should have learned in Calc 1. Arc length is equal to radius times the angle.